Welcome everyone to the second seminar of CosmoLATAM. Uh, I'm very happy to to the people who speak here. Today, uh, our speaker will be Belén Costanza. She is finishing her PhD in Universidad de La Plata. And the title of her speak is Deep Learning Applications in Cosmology from the Early to the Late Universe. So, Belén, you can start. Thank you.
Okay, thank you. Thank you, guys. Thank you for the presentation and thank you for coming here. So I'm going to start, and as Francisco said, I'm a PhD student in Argentina. I'm working under the supervision of Professor Claudia Scoccola. Some of you know her. And yeah, my presentation is about the deep learning application that I made during my PhD. I didn't finish yet, so I have many things to do. Okay, so the idea of the presentation is to start talking about the neural network that I developed for the CMB pipeline. So I'm going to start from the early universe and the motivation of using neural networks. Then I'm going to change to the late universe and talk about a deep learning application in the large case structure, specifically in the problem that I worked in, which is about the inference of the wonder matter mass. I mean, the inference of the nature of the dark matter using neural networks. So this talk is like divided into two main themes, which is the CMB in the early universe and the large case structure in the late universe. Okay, so this is just a very brief introduction because I think you already know all of this. So, as we know, the CMB is the relic radiation from the early universe, which is released at the recombination epoch at redshift 1100. It has a black body energy spectral distribution with a temperature approximately equal to 2.7 Kelvin, but the CMB presents anisotropies that comes from the metric perturbations of the universe, and the scalar metric perturbations give rise most of the CMB temperature and polarization anisotropies, but the tensor metric perturbations also give rise to a unique feature in the polarization of the CMB. In this picture, I'm just showing the map of the CMB, the temperature map of the CMB in the entire sky measured by Planck collaboration. And each point is, in each direction, is a different value of the temperature because these are the anisotropies. And this is the power spectrum of the measured power spectrum also by Planck. Um, Okay, so as I say, the CMB also is polarized, and this metric perturbation also generate a quadrupolar anisotropy of the radiation field, and when the photons interact with the electrons by Thomson scattering, they generate the linear polarization that we see in the CMB, and specifically the tensor perturbations in the metrics generate a specific pattern of the of the polarization of the CMB, which is the B modes, and the polarization of the CMB is mostly characterized by the E and B modes instead of the Q and U parameters of Stokes, and will be like a measure goal now in cosmology to measure these B modes. Because are not measured yet. And different instruments and collaborations in the world try to measure this because it will be like an indirect measure of gravitational waves generated during inflation. So I put here some collaborations and instruments that try to measure these B modes. One of them is the Cubic Observatory, which is a collaboration with an instrument here in Argentina, in Salta specifically. There are another ones like Simon's Observatory, which is in Chile, CMBS4, I think it's also in Chile, and Lightbear. Okay, so given this motivation, how we measure the CMB now, how is the process of taking information, cosmological information from the CMB? Well, under the assumption of the lambda-Calder matter standard model of cosmology, we know that the CMB is mostly a Gaussian random field, which means that the summary statistic of the two-point function summary statistic, which is fully described by the power spectrum, carries all the essential cosmological information. So using as is a Gaussian random field, we can use the power spectrum to extract uh, mostly all the cosmological information. So this is like the typical way in which the how to analyze the CMB. It starts from a TOD, which is a time ordered data measured by an instrument that make an scanning of the sky. And then there is a process called map making, in which these TOD are converted into maps, like the maps that you are seeing here. And in this step, there is a compression of the information because you are like, instead of having the TOD, which has this very huge number, you have a map with a lower number. So in this compression, it is important, in each of this compression, it is important not to lose important cosmological information. That's why it's necessary that each steps being as optimal as possible. Then after having the map, we can measure the power spectrum, which is, as I say, the summary statistic that brings the cosmological information. And then with the power spectrum, we can estimate the cosmological parameters. So we have like 10 numbers here compared with this huge number, so it is a lot of compression, and that's why it's necessary, as I say, each step being optimal as possible. So in this step, when we have a map of the CMB, it is not a clean map. We can have like foregrounds from the galaxy, for example, and also we have instrumental noise for the measured device, like an instrument. So in this step, there are another process in the pipeline called like component separation to separate the foregrounds from the CMB, and another one called the Wiener filter, which is the filter that reduces the noise present in the maps. I will talk about mostly about this Wiener filter using neural networks because it's the method that I work a lot in my PhD, and but there are several like trials to perform neural networks in each of these steps and also in component separation. Okay, so what is the Wiener filter? Why is important to have it in a CMB pipeline? Well, the Wiener filter, as I say, reduce the noise present in the signal and try to reconstruct the signal behind without noise. So suppose that you have like a CMB map, which is the data. Well, the data will be like the sum of these two terms, which is the signal uh, times the R, which is the response matrix of the instrument device, plus the noise. So we want to reconstruct the signal. I mean, the map of the signal of the CMB with the noise reduced. And the Wiener filter estimator is a well-known estimator, which is of this way. This is the Wiener filter estimator. This is the data. So it is linear with the data. And these are the covariance matrix of the signal and the noise. And I didn't put here all the formulas, but this estimator is obtaining by minimizing the residual between the signal realization and the optimal and the reconstruction. And also, this estimator coincides with the maximization of the conditional probability of the signal given the data. So you want to maximize this posterior, which is as I say, the conditional probability of the signal given the data. And when you maximize this, it's the same as minimize what is inside the exponential factor. And when you do that, you will obtain this same Wiener filter estimator. That's why it's the optimal way to reconstruct the signal behind with the noise reduced. Of course, the noise you can never subtract completely, but doing this, you can reduce so much the noise. Well, you have to invert these matrices if you want to calculate this estimator, but these matrices can be very huge and very difficult to invert. Usually it's performed with the algorithms called preconditioner conjugate gradient. I don't know if you already heard about that. It's present in many different algorithms of the in the in see, sorry, who's talking?
Someone has a question? No?
You can
Okay.
interrupt me, but I cannot see you, so you have to stop me by talking. Um, okay. So, as I say, this is a very computational cost. This is very expensive to do in terms of the computational cost. So we try to make this binary filter for the CMB, but using neural networks. And as I say, if you minimize this chi-square function, if you minimize properly, you can obtain the binary filter estimator as close as possible. So if I'm using a neural network, I will use like the loss function will be the same expression. And I write it here, the expression of the loss function, which is the same as this one. Change it just a bit, the notation. This is the implementation for temperature maps or for polarization maps. In this term, this is the term in the configuration space. This T and N is the output of the neural network, and this is the observed CMB temperature map with noise, mask, and so on. And this N is the variance of the noise in the configuration space. So this is this term. And the second term is this is the covariance matrix of the signal in which it is diagonal in Fourier space. That's why this term is written in Fourier space, and these are the CLs, are the power spectrum of the signal of the CMB. This is the implementation in polarization map. In this case, you have two terms, one in the configuration space, one for the Q and another one for U. And the Fourier space term is written in terms of the E and B modes, because as I said, we usually, for polarization, in Fourier space, we work with the power spectrum of E and B modes. Well, in this, I will focus in this presentation about the polarization because it is like the most important thing now in I mean in cosmology in the people that works with CMB. So the input will be Q and U maps with noise and a mask. And the output will be, if you minimize properly this loss function, you will obtain a map, a binary filter map of Q and U that you can transform and obtain the E and B modes map of the binary filter. So this is the neural network that we developed. We put a name called Deep Binner. It is based in a previous neural network called BinnerNet, which is an autoencoder. But this case, the BinnerNet only consider a very simple case of noise, which is an homogeneous noise. And it was written in Python 2 and TensorFlow 1.1, which is obsolete now. So in this case, in our neural network, we include more complex models for noise. So we have to change the architecture of the neural network, and we write it in Python 3 and TensorFlow 2. We also write it in PyTorch, but I will put here the result with the TensorFlow, but the PyTorch result were mostly the same. So I studied a lot just the this neural network for temperature, but I'll let you hear the paper in which I present this result. I studied a lot the performance and efficiency, but I will, as I said, I will focus here only on polarization. And yeah, so as I say, this is an autoencoder. It is composed of layers that are convolutional neural network, convolutional layers. So you receive a map which has the noise and the mass. This is the observed map that you have of the CMB, and goes through this channel. It will be like compressed, and then in the encoder part, and then it will be like expanded in the decoder part, and the return is a map of the same dimension as the input. That's why it's an autoencoder. And this channel, it is a linear channel because as I showed you in the past, the Wiener filter estimator is linear with the data. So we wanted to perform like the same as the Wiener filter. That's why we made this channel to be linear. But in order to help the neural network in order to improve the performance, we also add two channels that multiply the results of the linear layers. And these two channels have the information from the mask, which the mask is like an image of zero and ones. It's a binary mask. Well, when you have zero, it means that you don't measure anything. For example, if you want to remove point sources or that kind of stuff. And also we include a channel with the variance map. This is the inhomogeneous noise, uh, in which each pixel is a variance from which the noise will be realized from a Gaussian distribution with the variance that it is here. So the variance is different for each pixel. That's why it's an homogeneous noise. Okay, so work with polarization is not an easy task because we have the leakage problem when we have a binary mask. The leakage is like a transmissions from the E modes into B modes. So when you saw that you are seeing B modes, sometimes they are not B modes. They are contamination from the E modes, mostly in the regions in which you have mask. And this is problematic because you want to measure the pure B modes, and also the B modes have a power spectrum which is several orders or orders or magnitude lower than the E modes, and so that's why the B modes is like covered by the E modes, and we should clean this. We should clean the pure B modes from the ambiguous B modes because otherwise we are not seeing the scene that we want to see. Um, so working in this is difficult because I would like to, with the neural network, to reconstruct the signal of the E and the B modes. But the E is mostly covering all the polarization information. So we make like a procedure in which we train the neural network. I mean, we receive the Q and U observed maps with noise, as I told you. We train the neural network, deep binner. Then we obtain the result of the neural network, which we transform to E and B, from Q and U to E and B. And then we see how is the result of the E and B modes reconstruction. And in the first training, we mostly obtain the E map, which is expectable because, as I say, the E is mostly covering the B modes. So it is easier for the network to see the E modes instead of the B modes. So that's why we made like we made like an iteration in which we create a new data set with the E contribution removed. So we create a new data set, as I put here, Q and U observe ops, and it is remove the contribution of the E mode that comes from, well, from the first training. And you can, I mean, you can train again, and then the neural network now is going to see more the B modes. You are helping the network to focus on the B mode and not in the E mode, because you are removing what is annoying you. So this is just these are some figures that illustrate this. In this first iteration, in the first training, we are not seeing anything here. Here is the mask, and we are really not seeing anything. But going by several iterations in which we remove the emo contribution, we can see that, for example, in the iteration 4, now the B mode is like very, very clear that it is here. So that was the procedure that we made to obtain the B mode. And this is like the final result. I used a homogeneous noise from the Planck mission, which is a heat map. This is the inhomogeneous noise because I wanted to be as realistic as possible. Yeah, this is like an example. You have here like the E and B mode of the sky. This map doesn't have noise and um, a mask. This is the Wiener filter result using the conjugate gradient because I'm also use the conjugate gradient just to compare if my neural network was performed correctly. And this is the result of the neural network of the E and the B modes. You can see just by eye that these two maps are mostly similar. Maybe in the mask, this is the region of the mask, is a bit different, but in the inner regions, just by eye, these two maps seems very, very similar. But we want to quantify how much our neural network is working well. So we use this cross correlation coefficient, which is a coefficient that is measure how these two maps are similar. And these are the Fourier coefficient of the map, this A, and this is the Fourier coefficient of the Wiener filter, but this result using the conjugate gradient. And it is normalized, so if the cross correlation is equal to 1, it means that these two maps are mostly equal. And if they are not equal to 1, it means that it is bad. So I tested with different masks, different complexities of the mask, which will give different amount of leakage. And in this case, this red curve, you can see that this is the cross correlation for the BMO map, and it is like near 0.95 in the larger scales, so in smaller multiples, and then it goes mostly to 1. Um, yeah, these first scales are difficult, as I say, because of the leakage that affect mostly the larger scales. But we saw that it works like quite well. Of course, this could be improved if you make more and more iterations. You are going to improve even better. This is just like the E-mode contribution. As I say, we wanted to reconstruct the B mode and also the E mode. And in the first training, this is just by the first training, the first iteration, you already see a lot of E modes, but nothing about the B mode. And in several iterations, also you improve the contribution of the E mode. And when you improve the contribution of the E mode, you are subtracting better this contribution that you don't like, and you can obtain better also the B modes. Uh, I don't know if I'm clear on that, but ask me in any case. Well, this was the part of the neural network. I was able to perform a neural network that reconstruct the E and B mode, the signal of the E and B mode at the map level. But as I told you in the first slide, the next step will be to measure the power spectrum. This is a bit slow. Yeah. So having the maps, I would like to measure now the power spectrum. And I wanted to see if making this Wiener filter in an efficient way, I was able to estimate the power spectrum in an optimal way. So uh, when after training the network, I mean, train the network could take uh, some days, but when you have the network train it, the predictions are quite fast. So that's why it is more efficient. And to do the power spectrum computation, we should maximize the likelihood function, which is the likelihood of the data given this is the band power. It is like the BNet power spectrum, is the power spectrum average in a bin of multiples. And assuming a flat prior is proportional to the posterior of the band powers of the power spectrum given the data. We want to maximize this, and as the modes are Gaussian distributed, this is the expression of the likelihood. And where C here, the matrix C, is this one, And this matrix is not diagonal in any basis because the signal, I mean, the covariance matrix of the signal is diagonal in Fourier space, but the covariance matrix of the noise is, in case of uncorrelated noise, is diagonal in configuration space. So uh, make the inverse of this C matrix is very computational expensive, and this will be the result of the optimal quadratic estimator. I'm just putting here just to believe me. I will follow mostly the calculations from a paper of Euro Selchak. I left the paper here if you want to see more the calculations. I'm making just like a summary. And this will be like the optimal quadratic estimator. So if you are able to calculate this, you will obtain like the best power spectrum that you can obtain. But it is very common to see in the literature that there is an algorithm called pseudo-CL, and that it is used to calculate the power spectrum. And this algorithm assumes that the C matrix is diagonal, which is not true of what I said before. But it's okay. Assuming this, you can calculate the power spectrum in an efficient way, but it's not going to be very optimal. And I follow, as I say, the work of Urov Selchak, which is going towards an optimal way of calculate the power estimator and calculate this optimal quadratic estimator. I think it's not the idea to, well, I will try not to tell here all the steps because maybe I will confuse more. But the idea is to work with the maps, with simulations that I will call the latent variables, make the Wiener filter, and then marginalize around the Wiener filter solution. So if you have this posterior, which is the same posterior here, doesn't you don't have to see this lambda coefficient is not important here, and if you marginalize this posterior, marginalize in the latent variables, you will obtain this. So the idea is to do a perturbative expansion of this posterior around the Wiener filter solution and then integrate over it. Uh, just that. Well, as I say, if we have an expression for this posterior in terms of the Wiener filter solution, then we would like to maximize the posterior, or the likelihood is proportional because of the flat prior. I mean, we would like to find the most probable set of band powers given a set of measurements. And the idea here is to perform a second order expansion of the log likelihood, um, which I'm putting here, and then taking the derivative with respect to delta theta and equating to zero, you will obtain the expression for the maximum, which will be the optimal quadratic estimator, but a simulation based because I'm working with simulations. Why it is like a delta theta? Well, because this expansion is performed around a fiducial power spectrum. I mean, I will start for a fiducial power spectrum, and then I will try to measure a new power spectrum. I mean, I will receive a new map in which I don't know what is the power spectrum, I don't know what is the signal, because this map will have noise and the mask and so on. So I would like to estimate the power spectrum of this unknown signal. And I will start by a fiducial one. And then, as doing the steps that I said, I will obtain these two expressions for the optimal quadratic estimator. And I would like to estimate this delta theta. This F and B, well, B is the noise bias term, and F is the Fisher matrix, which is the covariance matrix of the power spectrum. I let here the expression of F. So calculating F through simulations, you can obtain the error of the power spectrum. And probably this expression maybe will remind you to this one, where this will be like the bias term, and this one is the Fisher matrix. And this one, it is expressed with a new notation, L, which is this one. And in this L, in this EL expression appears the Wiener filter map. So I will work now with simulations to estimate the bias, the fissure, and then to calculate this delta theta in order to obtain the true power spectrum. But as I say, I will start for a fiducial one. And finally, my true power spectrum, this is separated for E and B modes, will be the fiducial one, which is the one that I know, and this one that I estimate now. So this part, the important idea here is like having a binary filter that is efficient, we can calculate through simulations this Fisher matrix and bias matrix. The Fisher matrix is like a Monte Carlo average, and we'll need like 1,000 simulations or 2,000 if you want to be more accurate. So we need a binary filter to be faster, to be fast, because otherwise it will take forever and it is impossible to do. But using the neural network, working properly and making predictions with that, we are able to estimate the Fisher matrix in a reasonable amount of time. So the idea behind this is that using neural network, I mean, for this problem, no, you can estimate the power spectrum in a more optimal way that just assuming that the C is diagonal, which is not exactly true.
Sorry, Belén,
Yes, please.
can you hear me? Yes.
Yes.
What is the dimension of your theta space?
The theta, this one you are saying, right? The theta.
Yes.
Well, it can be. I mean, these are the power spectrum by bin. So you have like when you have the power spectrum, you have like, for example, 2,000 multiples. But as I will average in some bins, I can obtain like, I don't know, 100. It's like a choice. I don't know
Okay.
if I'm clear, but it will be like, yes. I'm using
So
usually 50, 100.
in the expression f theta, f l
Mhm.
l prime theta l, so the l should be the mm,
It's
multipolar
like,
number,
yeah,
but
it's like the,
you
yeah,
rename it and you bin it. You
yeah,
say
exactly.
one
Right
is
now,
from 1 to 100 and 2, I don't know.
yes. I mean,
Yes,
yeah,
okay,
yeah, yeah, exactly. I mean, it is bin now, so this L it doesn't, all the multiples in the power spectrum, it is like only 100, for example. And the L
great.
will represent only one multiple in the bin that you're considering.
Thank you.
Okay. Okay. So, yeah, I will just show here. Well, you can see here that this is like the relative difference between the measured power spectrum and the true power spectrum. I mean, I'm working with simulations, so I know what is the true power spectrum, and I wanted to test how well my code is, so my method is, so I compared the relative difference. And here is all the multiples, but you can see that are only these ticks. So these are the beans. I mean, I have only one bean here in 250. That is will like cover a range of multiples, and the so on continue for the other beans. And I mean, I'm not making this for all the multiples available, just for the beans. Um, yeah, so making the relative difference, I can see in this, for example, this orange one, that it is unbiased because it's around zero, but increase the error bars increase with to higher multiples, and that is because the noise cut the signal. I don't remember exactly when, but I think it was near here. And then when the noise becomes completely dominant respect to the signal, you cannot see mostly anything of the signal. So that's why the error bars becomes higher. But you can still, beyond the noise, still measure the power spectrum. So Yeah, the idea was just to tell that you can start for a fiducial power spectrum and then use the create the maps, use the binary filter with the neural network, and follow this procedure to estimate the true power spectrum of a new map with an unknown signal. That was the idea. And here I just wanted to compare with the pseudo CL because it's a library that it is used a lot in the literature and for the instruments. And I wanted to see how my method works compared with the pseudo CL. And considering an average of 100 maps, I saw that this relative difference that in the pseudo CL it was a bit biased compared to my method. Uh, is this the orange ones, and the other the the blue one is like my method. So it is the pseudo CL is more biased, but I would expect that because they are assuming some approximations, and also the error bars. Comparing the error bars, this yellow one is the errors in the power spectrum using the pseudo CL. Well, this green is also the pseudo CL, but these yellow ones use a purification method to work with the leakage, and the other ones the this blue and pink. Don't worry about why there are two. I didn't explain that. And are my method. So the error bars um, beyond this 750 is very similar to what I obtained. So it is mostly the same. But for larger scales, the error bars of the pseudo CL are really high compared to my method. So yeah, we were able to recover a better estimation of the power spectrum that we wanted to test. So I left here only the paper with all this information, and the conclusions until now is just like we can use a neural network to simulate the binary filter in this case, but it could be another method, and make an efficient way to perform this binary filter, avoiding this conjugate gradient. And thanks to that, it is feasible to calculate the power spectrum of an unknown signal in a more optimal way. Doing these optimal quadratic estimators. And the errors found are smaller than the errors estimated with the pseudo-CL. Yeah, just here I'm showing the advantages of using neural networks in the CMB pipeline. Of course, there are a lot of work to do yet. Okay, so I don't know which hour is. Okay. I will change the topic now because I talk about the early universe, as I said, using the observable of the CMB. But what about the deep learning applications in the large scale structure? So right now the large scale structure is different as the CMB because I say in the past that as the CMB could be treated as a Gaussian random field, you can just measure the power spectrum and it's the most important summary statistic to extract cosmological information. But it is not the case for the large scale structure because the universe evolves and the matter density um, collapse into halos, filaments, and voids. So the structure formation becomes highly nonlinear, and then the field cannot be treated as a Gaussian. So it is in a no Gaussian regime. So how can we extract information now, uh, compared with the CMB? And yeah, I saw in the literature that machine learning becomes like a promising tool to extract maximal information from cosmological field, from the large scale structure. And I let you hear also some papers that doing that. For example, this paper try to, well, predict the underlying cosmology, I mean, predict the cosmological parameters, considering using CNNs from galaxy properties. And this one is more focused on trying to predict the wonder matter mass and make an inference in the nature of the dark matter. But when you work with machine learning, you will need like a data set. You need to build a data set. And how do you build a data set? It's like in this scale from the large scale structure, it is complicated things to do. And I put here the DREAMS project, dark matter and astrophysics with machine learning and simulation. And this DREAMS project give a large suite of hydrodynamical simulations of the universe. So I use like one suite that include 1024 hydrodynamical simulations, specifically cosmological boxes. So now I will have like 1024 different simulations, like different simulation of the of universe. So these simulations track the evolution of dark matter particles and gas resolution elements in a volume from redshift 127 to redshift 0, and it will provide a large number of galaxies, so we can have having this huge sample, we can make statistical analysis. And the model of this hydrodynamical simulation is like an illustrious time G model setup, but it will have the cosmological and astrophysical parameters varied. That's the difference. So this suite will have all the simulation, but with different galaxy formation astrophysics and also particle physics models. This is the ranges of the varied parameters. These are the cosmological parameters, omega m and sigma 8, and also the parameters of the feedback of supernovae and HENs. And also, they will, in this project, one of the ideas of this project is to test with alternative dark matter models. So also they vary the mass of the dark matter in this range. And yeah, the idea, at least in my work, is to see if we can identify signatures of the influence of dark matter, alternative dark matter models, um, from this large-scale structure information. Well, this is a video, but usually these things doesn't work well. Can you see the video, right?
Yes.
Okay.
Yes, yes.
Okay. Well, I just uh, showing here one example. This is one example of this simulation. This is a simulation of the large-scale structure. This is just a single one. But I'm interested more in the final part of the video. Just coming. This is the part that I'm interested in. Yeah. So this is the data set that I have now. These are different simulations of universe. Of course, this simulation, each one will have a different value of the cosmological parameters, so are different realizations of universe. And these are the training set, these cosmological boxes. That's why I wanted to show the video, because I thought that was illustrative. Yeah, as I say, my objective most was focusing on predict signatures of dark matter, specifically warm dark matter. So using these simulations, I followed two procedures. One was to consider statistical properties of galaxy populations. Yeah, I use summary statistics, histograms, or the two moments of the distribution, which is the mean and the standard deviation, and try to predict a full posterior of the wonder matter mass given that summary statistics. I use neural network for that. I work with the multi-layer perceptron, then with the normalizing flow, that is a neural network that is able to predict this posterior distribution. And the other procedure I made was considering halos, single dark matter halos, because I wanted to see if there is information of the dark matter in more like a smaller scale in a dark matter halo. So in this case, I consider dark matter halos, which more than four subhalos. This was just a choice. So dark matter halos with more than 4 galaxies use a graph neural network and then again try to predict the posterior distribution using a normalizing flow. Um, okay, as I said, I build my data set, which are the simulation that I showed you in the past. I split the simulations in training, validation, and testing. Here I'm just showing for the first case, the statistical descriptors of galaxy population, like the histogram of the subhalo properties. For example, this is the case of the gas mass, and this will be the case of the total mass of each galaxy. And then then I tested with first 2 moments, the mean and the standard deviation of this distribution. And the second one was considering dark matter halos. In this case, I use graphed neural network. So these two are different graphed. So for example, you have this halo. This is a dark matter halo, and each purple point are subhalos inside that halo. And well, as I say, I work with I made 2 approaches, so I use different neural network for that. I put here like the figure of the paths that I made, but I will not explain now each of these, how the perceptron of the graph layer works. I left here some papers if you want to read more about the methods. But as I say, the idea is to use a summary statistic that could be the distribution of the galaxy properties in the simulation, then goes through a perceptron layers, a multi-layer perceptron that will create a latent space, and this latent space will feed a normalizing flow neural network, and we can obtain the density, we can obtain the probability, the posterior of the wonder matter mass given, given these statistical properties. This is like the a figure of the result. And the case for the halo simulation, you receive the graph that I showed you in the past. The graph contains the nodes features, which are the purple point. These are the properties of the galaxies. Also contain information about the connections between galaxy by using a distance criteria. And then also contain global features. Like a global feature of the graph. Then goes to the graph neural network, and again this will produce a latent space, and you can use it to feed the normalizing flow and obtain the posterior distribution of the wonder matter mass given the graph or given that specific halo. So considering the mass inference using global statistics, I use like a set of 14 properties, and I test with each one individually. These are the properties of the galaxies. And yeah, I tested just to use it one by one. And this is the result, like as I told you, this will be the posterior that you will predict. Um, so I found that the gas mass of the galaxy was the property with the best performance in the inference of the wonder matter mass. Here is the determination coefficient, which is this expression. And if the determination coefficient is equal or close to 1, it means that the predictions are very accurate. So I thought that was interesting. Finding that the gas mass of the galaxy were the most important feature for the inference of the dark matter. This I make the same, but considering the first 2 moments instead of the full histogram. So in this plot, I consider the median and the standard deviation of the gas mass, and in this one was the subhalo total mass. And you can see here in the x-axis the target, which is the true value of the wonder matter mass, and in the y-axis, the prediction. And you see that it is like following this one-to-one relation. And each point is the mean of the distribution, the mean of this distribution, and the error bars will be the standard deviation. So, as I say, the R square using the two first moment is 0.86, which compared with the subhalo total mass, that is equal to 0.71, it is higher. So the gas mass is like more informative than the subhalo total mass. And I think that was interesting because what we know about the wonder matter models, we know that it affects the small scale, the power in the small scales, and the abundance of smaller subhalos. So we know that it affect the subhalo total mass, but I didn't know that the gas mass also were so important. Well, this is just, I will try to skip this, but considering halo label information, I'm using here now the halos, single dark matter halos, but I using the halo information, and as global feature, I use the mean and standard deviation of the gas mass. So as global feature, I'm using the same information as here. And I wanted to see if including the information from a single dark matter halo, I could obtain a better result. And I saw that is an improvement because R square is equal to 0.88, but it is like very marginal. It is not so much because considering just the mean and standard deviation, the global features was 0.86. So that tells me that if you use single dark matter halos, you can obtain better constraints, but it is not so informative. The dark matter halos alone, you cannot use dark matter halos alone to predict the wonder matter. Uh, Mostly the information comes from the first moment of the distribution. Okay, so yeah, this is the final slide. Just as a conclusion, the important message here is that we can also use neural networks method to distinguish between alternative dark matter models. So I use it here to predict the wonder matter mass given large scale structure input. I found that the subhalo gas mass distribution provides the strongest constraint on the wonder matter mass. And well, I didn't speak about this, but I found that it's mostly the number of subhalos with zero gas mass, the key discriminant to distinguish between wonder matter from cold dark matter. So the one of the disadvantage of this neural network is like they are difficult to interpret when you obtain results. Usually it's difficult for me at least to connect with the physics. So why is happening this? But it seems that the absence of gas could be a tracer of water matter mass. Um, I don't know so much about this, but maybe it could be observations of the gas in the galaxies that could, in the wonder matter cosmology, could help to have information from the nature of dark matter. Um, yeah, so that's the general idea. I think my intuition say it is not so crazy obtain something like that because in the wonder matter cosmology, you will obtain you will have a suppression of a small scale power that will delay the collapse of low mass subhalos and shallower potential wheels. So probably these small subhalos will tend to accrete and retain less gas. That's why I think in the wonder matter cosmology, you will have more subhalos with absence of gas. And seems that this could be a tracer of an alternative model of wonder matter. And this all come from the neural networks. Um, so yeah, this is the last slide. That was the idea of the talk, just to show promising strategies for extract cosmological information using neural networks. In the first part that I talk about the CMB, I just show how to simulate an existing method with neural networks. And in this one, in the large scale structure, I'm showing how to use neural networks to extract the cosmological information directly from the fields. I'm not just here simulating a method like the binner filter and so on. Okay, so that's it. I hope it was a bit clear. Thank you.
Thank you, Belén, for your talk. Now we have time for questions. Someone has a question, please be free to do it.
Well, I tend to talk so much in the in the in the presentations.
That's okay. It's okay. Okay, I have a question. Maybe it's just a naive one. Um, in your first slides, uh, you mentioned that you train your neural network with
Mm-hmm.
the parameters of the Q and U parameters of the CMP, but
Mm-hmm.
you show this squared um, images of the CMB. I guess I'm correct of this.
What in which slide do you mean
Yeah,
these
this slide,
maps?
for example. Yes, these maps.
Mm-hmm. Well, these are maps of the CMB in a flat sky approximation.
Uh-huh.
So
Uh,
this is an important thing.
yeah,
Yeah.
why you're using the flat sky approximation and not using, for example, an
Uh,
expansion in spherical harmonics?
well, because it was easier. I mean, the biggest reason is why because I mean, I'm working here with the CNN. And a CNN receives a 2D image, so it makes a convolution in a plane. But this will be only true in the flat sky approximation. So it will be only true if you are seeing a small patch of the sky. But if you are using, I mean, if your instrument measure a patch of the sky in which the curvature becomes important, it's not something that you can ignore. Yeah, then you have to do the spherical harmonic transformation and expansion, sorry. And now this neural network, you cannot use it just like that. This what you're saying is the other part of my PhD. What I'm working now is to implement all this method, this deep binary method, but in the curved sky. Yeah. And I'm doing different things. One is to make a projection, a good projection of the sky, I mean of the patch of the sky, into a plane, and then use this convolutional neural network. Because sometimes work in the curved sky with, for example, with the graph neural network, it is very expensive. So I will try to make a good projection. But also the patch of the sky shouldn't be, it cannot be so big, you know, it cannot be the entire sky. So this won't work for Planck.
Yeah, super, super. When you finish this project, please come to us and present it.
I hope for my thesis.
Augusto has the hand raised. Okay, I will read his question. He said, maybe you mentioned it, but somewhere, and I didn't hear it. Did you do any estimation of the speed improvement that comes from
Mm.
using deep winner versus the standard method?
Yeah, yeah. I made it, but I didn't mention here. I mean, I just let you to believe me. But yes, I made it in exactly in this paper when I work for temperature maps. No, I mean, I also made it for polarization, but mostly I made market analysis in this paper, in which I compare having the neural network trained. I compare the predictions in a set of maps, and always the neural network is faster than doing the conjugate gradient in each map. So of course you have to train and this take times, but even having the time to train the network, you train only once and then you can do the predictions of whenever a data set of any size that you have, and this will be faster than doing the conjugate gradient. And the important part is what I said about the power spectrum is when you estimate the noise bias and the Fisher, you have to do simulations, and in each simulation you have to do the binner filter. But the network is already trained. You train it only once. I mean, it takes time, but it was only once, and then you can make the predictions efficiently in each map. And if you wanted to do it with the conjugate gradient, making a conjugate gradient in each of this map, it will be impossible to do. So that's the improvement of using the neural network. But I didn't mention it here. I say that was efficient, but I didn't mention the results that prove that. I know.
Okay, more questions? Please be free to.
No, thank you. Thank you for the question.
Belén?
Mm-hmm.
Yes, I got involved in your explanation about the curved sky.
Mm-hmm.
Uh, so are you planning to do like a stereographic projection to convert it to a plane?
Well, I'm testing with several projections. Uh, when you make a projection, I don't remember now the stereographic. I know the relation between the transformation coordinates. I mean, coming from the sphere into the plane. But when you make a projection, you will distort the map, of course. It is
Yes.
impossible to avoid the distortion. And I'm trying to see now, I mean, my work now is trying to see if how this distortion affect the operation, like the Wiener filter one. Yeah, the operation that I want to do. I mean, how this distortion are so important in the things that I want to do. That's why I'm searching for the best projection. For example, I tested with the genomic one, which, if I understand correctly, is like a tangential projection. I mean,
Mhm.
in polar coordinates is the radius is the tangent of the theta angle. And I saw, for example, that this projection was really bad. I mean, the Wiener filter was awful. So I cannot use the genomic one. I think the stereographic is the tangent of the theta divided by 2. I think so. I have to check. But I didn't test it. I tested another ones, another projections that was better. I mean, the result working in the plane was really good. And then returning to the sphere was like uh, making the same in the sphere from the beginning. But yeah, I'm working in the
Okay.
in this. Thank you.
Yes, because the
And
great thing
thanks.
about the stereographic projection is that it's a conformal transformation.
Mm-hmm.
So any line on the sphere
Mm-hmm.
get projected to a circle on the
Mm-hmm.
plane.
Mm-hmm.
Yes, think for example in the equatorial line.
Mm-hmm.
Yes, it, it is a line on the sphere.
Mm-hmm.
You project it is a circle,
Okay.
and any other great circle in the sphere
Mm-hmm.
projects to another circle in the plane.
Mm-hmm.
So
Yeah.
that's an advantage. And well, you the the relation between a circle and the other projected circle is given by a conformal transformation,
Mm-hmm. So you are
the,
saying that
the
making
conformal
this.
group in two dimensions.
Mm-hmm. Mm-hmm.
So in any case, I wanted to mention just if you see that it's useful for
I
your
didn't
future
test the
research.
stereographic, but I should. I should see. I mean,
Yes.
how this conformal transformation distort the pixels and mostly the neighbors between pixels, and see if this distortion is important or not. Probably it's going to be better than genomic of what from what you're saying. So yeah, probably will be. But I should test that. Thanks.
Okay, more questions? Okay, if it's not, let's thank again Belén.
Thank you, guys. Thank you. Thank you for hearing.
Uh, Great presentation, and we are seeing to get again at September 24th with another seminar. Please follow
Thank you.
the social media, social network, and like and subscribe in YouTube, please. And see you in 2 weeks.
See you
Goodbye.
guys. Thank you for
See
connecting. See
you.
you.